So previously, we started our discussion for shear and moment in beams, and then we answered up to number 2. So today, we'll just continue our solution for number 2. Once again, you have your beam, and the goal here is to draw the shear force and bending moment diagram for the beam. So we've solved for reactions already. We got up to your 880. So now I've continued the solution, so you just need to listen for now. So after writing your reactions, you're gonna start with your shear diagram first. So draw a straight line, that's your 0 mark, and then use your equation. So let's solve for the next shear force for every support or for every beginning and end of each force. So the next support will be at B, so let's solve for shear at B. Okay, to get that, you're starting with the previous shear force, so that's 0, since there's no reaction here. So we're starting with 0 minus, since forces are downward, area of this. So 0 minus base times height, 400 times 2. So you get negative 800. And remember, for every shear diagram, you increase the degree by 1. So if you have a straight line here as your load, your next diagram would have a diagonal line. So this negative, so you go downward, then that's your negative 800. Next, there's an applied force here upward. So you're just going to go up by RB, and RB is 1,520. So negative 800 plus 1,520, you get 720. Next, there's no force between B and C, so that's just a straight line. And then there's an applied force here at C, 400. So from 720, you subtract 400, since it's downward, you'll get 320. Next, the following support after this point C is your D. So to get shear at D, again, your previous force, 320, forces are downward, so minus the area of this diagram. So that's 400 times 4. So 320 minus 200 times 4. You get negative 480. Once again, there's a straight line, so you go down, you'll get negative 480 here. You have your reaction upward, so you're going to go upward, so negative 480 plus RD, which is 880. Negative 480 plus 880 is 400. And now, we're going to go to the next point, which is at E. So shear force at E. So that's 400, again downward, so minus area. So base times height, 2 times 200. You'll get 0. Okay? That's also one way to find out if you did your shear diagram correctly, if you start and end at 0. Afterwards, you're going to move on to your moment diagram. So once again, starting at 0, since there's no applied moment here. Then we're going to base our answers on your shear diagram. So from 0, the next point will be the same, your point B. So since this is downward, the area here will be negative. So therefore, moment at B would be, again, starting with your previous moment, so that's 0, minus, since it's below your 0 line, so minus the area of your shear diagram. So this is a triangle, so 1/2 base times height. So 0 minus 1/2 base is 2, height is 800. And you'll get negative 800. Once again, our graph is 1 degree higher. If this is a slanted line, your next line would be a parabolic line. So that's why it looks like this. So negative 800. Next, moment at C. So at this point. So at this point, your area is above your axis, so that's positive. So you're going to do negative 800. So negative 800 plus area of this. It's just a rectangle, so base times height. Base is 1, height is 720. You'll get negative 80. Since your area is upward, your graph would be upward as well. Okay? So this is a negative slope. This is positive slope. So you get negative area. And then for positive area, you go up. Okay? So that's why you go up until you reach negative 80. Next is here actually at this point. because after this point, your area becomes negative as well. So even though it's not a point existing on your original figure, it's a point of importance because of your shear diagram. Again, because your area changes. So that's why I added point F here. So to get moment at F, once again, your previous moment, so negative 80, this area is still upward, so plus 1/2 base times height. So 1/2 x times 320. Now, the problem is, how do I solve for x? You solve for that using your ratio and proportion. We have two similar triangles. So let's start. Base over height equals base over height. So base of this smaller triangle over height, which is 320, equals base of this. So that's just total length 4 minus x. So that's why this is 4 minus x. And then this height, which is 480. Solving for x, you get 1.6. Sub that into this equation, you'll get positive 176. So once again, your area is positive. Therefore, your slope for the next diagram should be positive as well. So you're going to go upwards once more. So from negative 80 going upwards, you'll get 176. So positive 176 here. And then after this point, your area becomes negative for the shear diagram. So your slope now should be downward. Once again, positive slope for positive area, negative slope for negative area. So now the next point of interest is your D. So let's solve for moment at D. So getting your previous moment, so positive 176. This area is negative, so minus. That's again a right triangle, so 1/2 base times height. 1/2 base, this is 4 minus x, so 4 minus x times height, which is 480. Solving for that, you get negative 400. So that's why here, again, negative area, so negative slope until you reach negative 400. And then finally, moment diagram or point at E. So we're solving ME. So copying your previous moment, negative 400 plus since positive area. And again, right triangle, so 1/2 base times height. 1/2 base is 2, height is 400. And you'll get 0. Positive, therefore again, positive slope, you go this way until you reach 0. Once again, that's another way to find out if you did the moment diagram correctly. If you start with 0 and end at 0 when there's no applied moment in your free body diagram or load diagram. Okay, so that's number 2. Any questions for number 2? Please answer in the chat. How about the others? Please answer as well. Okay, good. So basically, it's just getting the area of the diagram above what you're working on, and then minding your sign. So downward, negative. So your slope also is negative. Below the 0 line areas are negative, and then slope of your moment should also be negative. Right, since you don't have any questions, let's move on to the next topic, which is stresses in beams. So now we're done creating your shear moment diagram. Now, the reason why we're doing that is to figure out the stresses in your beam. So that's going to be based on the diagrams we've made earlier. So we have two basic stresses in beams. First is flexural stress, next is shear stress. So flexural stress is the normal stress due to bending of member. So hence flexure, bending. Shear stress is developed during bending to balance uneven horizontal thrusts between sections. Okay, so for example here, you have flexural stress and shear stress, flexure due to bending, and then there's going to arise, or there's going to result to a shear stress along the fibers of this beam. So these are the equations that we'll use for flexural stress. And then next, we're going to talk about shear stress. So for flexural stress, we have your moment curvature relationship. So 1 over rho equals m over ei, where rho is the radius of curvature for the deformation that your beam will experience along an element. M is the internal bending moment on that point. E is modulus of elasticity, and I is moment of inertia about neutral axis. So that's why, again, we're talking about moment of inertia as well in your Mech 30, because this is where we'll use that, if you remember Mech 30 subjects. And then stress is equal to negative my over I. I'll talk about why that's negative later on. So m is again just the internal bending moment about a point where you want to get the stress. Y is the distance of element from neutral axis. And then I, again, is the moment of inertia. And then if you want to get maximum stress of a beam, you get M. M here is the absolute value of the maximum bending stress that you'll solve for in the shear moment diagram. Okay, so that's where that will come in, here in getting maximum M, as well as here in getting internal M. C is the distance of extreme fiber from the neutral axis. And then C is the maximum value you can get for Y. Later on, again, I'll show you. And then another equation is M over S, because I over C is known as section modulus. If you know the section modulus of a beam or a cross section, you can simply use the equation M over S. So you don't have to solve for I anymore. And S is, again, just I over C. We call that section modulus. So let's talk about how that came to be. Or why is there a negative in my equation? So remember, we have the sign convention, positive for tension, negative for compression, right? So for example, here we have this beam. If we draw this moment, in order to create this is a smiley face. The moment associated with smiley face is this way, right? And this is a positive moment, right? If you create a smiley face, you create positive moment. And then here at the top, we have compression. This point is above your neutral axis. The neutral axis is this dotted line. Since it's above the neutral axis, we have sign convention for that as well. Distance y would be positive as well. Okay? And then these two situations create compression. And compression is negative. Okay, so negative stress, which is in compression. So that's why there's a negative here, because it just signifies that when your y is above the neutral axis and then your m is positive, you'll have stress in compression. So you're going to solve for this. Okay, if your answer is negative, that means on that portion of your beam, you're experiencing compression. Now, for example, using this equation, m is positive, we're still using positive bending moment, and then y is negative. So that means it's below your neutral axis, is somewhere here. This portion is in tension. Okay, and then the answer that you'll get will be positive. Okay, because stress equals negative my over I, right? If m is positive, so this is still positive, y will become negative. I is always positive. Negative and negative will cancel out. Your final answer would be positive. And positive stress is tension. Okay? So the negative sign there just tells you whether your stress is in compression or tension. Okay? And then what about that y and c? So to illustrate, let's say we have cross-section of a rectangular beam, and then this is your neutral axis. So y is just the distance from your neutral axis, okay? So let's say this point. So at this point, this is your, at this point, distance from your neutral axis to that point is your y. Now looking at our equation again, if we recall, sigma equals my over I. Therefore, the larger the y, the larger your stress is, right? And the largest y you can get is up to the top edge or outermost fiber of your cross section, right? So this is the farthest we can go from your neutral axis, and we call that C. So C again is distance from neutral axis to outermost fiber. So that's why sigma max, maximum stress, occurs at the edge. And that is MC over I. Okay, which makes sense because look here, at the edges of your beam, right? This point compresses the most, and then this point stretches the most. So those points are where maximum stress would be. Okay? So that's why our equations are like that. So we won't derive the equations anymore. Just remember these. So now these are the basic section modulus for different shapes. Again, section modulus is S used in sigma max M over S. So for a rectangle, S is BH squared over 6. For a solid circle, pi r cubed over 4 or pi d raised to 3 over 32. For a tube or ring, it's pi over 4 capital R for outer radius times outer radius raised to 4 minus the inner radius raised to 4. For a triangle, whether right or not, we have BH squared over 24. And then, once again, we have your area, a moment of inertia about X and Y axis. So for a rectangle, should have memorized it by now. Moment of inertia about centroidal axis for a rectangle, whether Y or X, is just BH cubed over 12. Okay? So if you're at Y, it's just the opposite. So instead of BH cubed, you have HB cubed over 12. And then for a triangle, it's BH cubed over 36. For a circle, it's pi d to the 4th over 4. And then for a ring, so that's just outer diameter over inner diameter squared. And then for a semicircle, okay, Ix, this moment of inertia about the base. Oh wait, yeah, about the base. If you want to get moment of inertia about the centroidal x-axis, if you remember again, it's 0.11 r raised to 4. So the equation shown here is only about the base x-axis or about the diameter of your circle. So the x and y-axis are already drawn in the figure, and these equations are in relation to that. So we'll use that table as reference in our following equations. Let's start with number 1. The simply supported beam in the figure has a rectangular cross-section 120 by 200 millimeters high. Letter A, compute the maximum bending stress in the beam. So let's focus on that first. Maximum bending stress. And to get maximum bending stress, we'll get the moment diagram or bending moment diagram. Okay, so let's begin. So try to draw guidelines along points of interest. Usually, those are at, again, supports and at application of forces. Okay. So the reactions are already given, 14 and 19. So I don't need to solve for that for now. So let's start now with the shear diagram. Again, starting at 0. There's an upward force here, 14. So you go up by 14. Yan. Next, shear at B. So VB equals 0. We have downward force here. So minus, and then area of that, that's 6 times 0.8. Oh, wait. The Nice. That's 4.8 now. Okay. Wait lang. Let me delete that. Oh. Hmm. 0.8, not 8. Oh, sorry, not 0, 14 pala, my bad. We're not starting at 0 because there's already an existing force here, or existing value for shear at the beginning. So 14 minus 6 times 8. So that's 9.2. Okay? So we're going to go down, right? Because this is a straight line, so the next diagram would be a slanted line. Next, point D. So shear at D would be the previous one. So instead of basing it on 92, 9.2, so here it's 9.2. Since there's no force in between, okay, you can just start from the beginning of your force, so at A. So equals VA, which is 14 minus 6 times total length 2. Okay, and that is 2. So you're gonna go down till you get 2. So this is 2 again at a slanted line, and again this is your 9.2. Since there's no force in between, it should be a straight line across all points. Okay, now we have an applied force here, 15. So you're going to go down from this point. So 2 minus 15, that's negative 13. So negative 13. And then at E, shear force at E. Okay. So negative 13 minus, then we're going to take this area. So that's 15 times 1. 6 times 1. And that's 19. So you're going to go downwards again until you reach negative 19. And then at this point, there's an upward force of 19. So you go up. So negative 19 plus 19, you end up at 0. So this is your shear force diagram. Okay, and that's not what we need. What we need is the moment diagram. So let's start doing that. So again, starting at 0, there's no applied moment here. So you're indeed starting at 0. Next, okay, this is a positive area. So moment at B would be so 0 plus area of this. This is a trapezoid. So to get the area of a trapezoid, that's base 1 plus base 2, so 14 plus 9 over 2 times length. And this length is 0.8. Please solve what's the answer here. Oh, 9.2 pala. 9.2, not just 9. Correct, Beatrice and Janelle. So Flores, Pascual. It's 9.28. So 9.28. So this is positive, therefore you're going to use a positive slope. And then you're going to go up until you reach 9.28. Yan. Okay. Next, moment at D. So moment at D, so from 9.28, plus, since you still have a positive area, and then area of a trapezoid, again, base 1, so 9.2 plus base 2, which is 2, over 2, times this length, so that's 2 minus 0.8, that's 1.2. Please solve what's the answer here. Correct, 16. Correct, Beatriz and Sierra. Gutierrez, Pascal. Okay, so positive 16. So you're going to continue to go upwards until you reach 16. Yan. So I forgot to write, this point is 9.28. This point is 16. Okay. Next, moment at E. So now this is below your zero line. So that's negative area. So 16, ME is 16 minus area of that. So base 1, 13 plus 19 over 2 times this length, which is 1. Please solve. What's the answer? 0. Correct. So correct. DMA. Okay. So we're gonna go down. So since this is a negative area, you need to go or use a downward slope. So we're gonna do that until you reach 0. Yeah. And that's your area. So this is 0. So you're gonna use this graph, and the highest point in the graph is your maximum moment. So can anybody give me what's M max? Correct, Sierra and Bea. So also Rika, Diana. So to get the maximum, you're gonna get the highest point, right? This is your highest point, and you already know that's 16. So M max is 16, and then our unit is kilonewton meter. Okay. Now that we know that, so that's your letter A. And that's just your maximum bending moment. At letter A, we're looking for maximum bending stress. So bending stress is the same as flexural stress. So that's all. I'll just move this here. And so letter A, maximum stress is MC over I. Max. MC over I. Right? And then M max is this. Now, standard unit for stress is Newton millimeter, right? So I need to convert this into Newton millimeter. So times 1,000 times 1,000, that's 10 raised to 6. So 16 times 10 raised to 6. And then can anybody give me what's C, considering this is the section of your beam? Remember, C is the largest distance from the center to the edge of your beam, of your cross section. Again, what's the value of C? Considering this is the cross section of your figure. In millimeter, since standard unit is Newton millimeter. Oh, it's kilonewton, then meter to millimeter. So 1,000 times 1,000. Kaya 10 raised to 6. Again, let's go back. This is your C. From neutral axis up to the edge of your cross section. In that case, since it's the cross section, what's C? Correct, Rika? Anyone else? Correct, Mooney. Okay, so once again, C is just distance from neutral axis to base or to edge. So that's given. It's 100. 100. Okay, so again, this 10 raised to 6 is kilonewton to newton and newton to meter to millimeter. Okay, so 1,000, 1,000, that's 10 raised to 6. And then this is the cross section of a rectangle. Can anybody give me the equation for the moment of inertia of a rectangle about its neutral axis, which is the centroid? Very good, Bea. Anyone else? Centroidal moment of inertia of a rectangle. Wala. So try to memorize it because we're going to be using this a lot. Centroidal moment of inertia for rectangle is BH cubed over 12. Okay? Base of this rectangle is 120 millimeters. Height, total height is 200 millimeters squared over 12. Please solve for this. What's the answer? Correct? Hmm? Cube, sorry. Kaya pala. Cube. Yes. Correct. It's 20. So who got it first? So correct. Yeah, Bea, Sierra. Wala pang 2 points. Janelle, Julia, Solomon, Flores. Okay, it's just 20. And again, all our units are in Newton and millimeter. So this is MPa for stress. Okay, so unit is the same even though this is like shear stress. Okay, MPa pa rin. And then how about letter B? Compute the bending stress at a point on section B. This is your section B. That is 25 millimeters below the top of the beam. So what does that mean? So bending stress at a certain point within your cross section. So that's not maximum. So we're not using MC over I, we're using MY. Okay, where Y is distance from neutral axis to point in question, which is 25 below top of the beam. So let's draw that first. If this is your beam, right? This is a cross section. This is the element that we're looking for. So this is 25 millimeters below the top. Okay? And then the rest, total is 100. So 100 minus 25, 75. Okay? And then to be more specific, we're looking for stress at section B. So meaning we need to get the moment at B. Luckily, we've already solved for that. It's this point. Okay? So MB is 9.28. Now, what if we didn't know how to do that? Like, we didn't solve for 9.2 and 9.28. What if I just did 14 and 2 directly because I forgot or I ignored this point B? What you can do is ratio and proportion. So once you know 14 and 2, okay, use your right triangles. So similar right triangle here and similar right triangle here. Okay, so height over base equals height over base. And you'll get 9.2. And using 9.2, you can get stress at B, which is 9.28. So we'll just do this equation. Okay? But since we already solved for that, we don't have to go through that. It's 9.2. And then unit is kilonewton meter. Okay? And now we can solve for stress. So stress at B is my over I. To be more specific, MB y over I. MB, again given 9.2. Kilonewton meter convert to Newton millimeter, that's 10 raised to 6. Y, can anybody give me the value of Y? What's Y? Again, Y is distance from neutral axis to point in question. Good, Bea and Sierra. Anyone else? Yung wala pang points. Correct, Janelle and Rika. Sino pa? 2 points na din ata kayo. Wala. Hey. Neutral axis. This is your neutral axis. So distance of that to point in question. Along the cross section. Okay. So I'll give it to, so correct, Bea, Sierra. 3 points ata kayo. Ano? Okay. Correct, Sierra. 4. And then Flores. Okay. It's already here. 75. Again, Y. Distance from this line to point in question. Point in question is 25 millimeters below the top portion. So this is 25. Total length of this is 100. So 100 minus 25 is 75. And that's the distance of your point to the neutral axis. So 75 over I, which is again moment of inertia, and we already know 120 times 200 cubed over 12. Please solve. What's the answer? Please include the sign as well. I didn't get the sign. It's negative. Negative. Correct, Audrey. And Wells, VMA, Vergara, Manrique. It's 8.7. So negative 8.7, because again, our equation for shear flexure stress is negative my over I. So negative 8.7. So remember, this negative sign just means your stress is either in compression or tension. Negative, therefore, compression. So negative MPa or 8.7 MPa in compression. There. That's number 1 for stresses in beams. Any questions so far? Please answer in the chat. None. So let's move on to number 2. Okay, number 2. The cantilever beam in the figure is composed of 2 segments with rectangular cross sections. The width of each section is 2 inches, but the depth are different, as shown. Determine the maximum bending stress in the beam. So again, maximum bending stress meaning we need to get the maximum bending moment first. So we're gonna do shear moment diagram once more. So cantilever, it's not simply supported. So remember, when we have a cantilever, that means there's gonna be reaction here at D, okay? And not only that, there's gonna be moment. So you can just guess the direction, or in this case, it's easy to actually know the direction of your reaction because it opposes the applied forces. Downward, upward, this is gonna create counterclockwise, so we need a clockwise moment to counter that. Okay, so RD is just 2000 as well, since there's no other forces here. If you do summation of forces Y, you'll get RD is 2000 as well. So now the only problem here is to get moment. So to solve for moment, that's just summation of moment equals at B, okay, equals 0. So 2000, that's counterclockwise, negative 2000 times total length 8. We have an applied or reaction M here, which is clockwise, so plus M equals 0. Therefore, M is negative 16,000 pound-inch. Okay? Rather positive. Positive, therefore, correct assumption of direction. It is indeed clockwise. Afterwards, we can now create our moment diagram. But first, let's start with the shear diagram. So we're going to create guidelines again at points of interest. So application of force, as well as where your cross-sectional area changes. It changes at this point. Okay. So starting with shear, draw your straight line here. There's a downward force, so go down by 2000. So this point is 2000. There's no force in between, so you just go a straight line. And then upward force, so this negative 2000 as well, plus positive 2000, you're ending up at 0. So that's an easy shear diagram. Next, moment diagram. So there's no applied moment here, so that's 0 or moment reaction. Okay, your area is downward. Okay, therefore my slope is downward as well. This is a straight line, so my next is diagonal this way, right? So it's just a straight line downward since there's no other forces in between. Now let's solve for that. So moment at D equals 0 minus base times height. Base is 8, height is 2000. So that's negative 16,000. So this is negative 16,000. And then you have an applied moment here, or rather reaction moment, which is positive 16,000. So you're going to go up positive 16,000, and then you're closing at 0. Okay? And that is your moment diagram. Now, the question here is maximum bending stress in the beam. So we don't know yet if the maximum bending stress would be here or here. So we'll solve for both. Okay? So let's solve for AB and max. Okay, so here, this is your AB. So we're only concerned with this shear diagram. So obviously, the maximum moment here would be the highest point, in this case, the lowest point, or rather, the largest value of moment. So it would be here, so MB. Okay, so M max for AB is equal to MB. And we didn't solve for MB, right? So you can do one of two things. You can either do ratio in proportion, since we know this is 4, this is 8, 0 and 16, or 0, 16,000, or you can just solve for that. So MB equals previous moment, 0, minus area above it. So MB, so we're only concerned with this area. So 2,000 times 4, that's negative 8,000. So negative 8,000. Okay? And then let's solve for maximum moment for BD. And max, what's the maximum moment of BD within this section? What's the maximum moment? If you look at your moment diagram. Anyone? Maximum. Correct, Sierra and Rika. Dianya and Gutierrez. Right? Sierra. Yeah. Gutierrez. Where are you getting these forces? Where are you getting your answers, guys? Okay. So M max. Again, maximum moment depends on your shear moment diagram. Okay? So this is the shear moment diagram for section BD. So we're gonna look for the largest value. And that's this point, right? This is the largest value out of all of these points. So that's 16,000. So that's MD, negative 16,000. Yeah. Now that you have that, you'll just use your shear, a flexural shear stress equation. So let's start with AB. Okay. So once again, AB, let's draw that. We have uniform width 2 inches. So this is 2 inches. And then height for AB is 4. Okay. And then maximum shear stress. So you can use MC over I, or you can also use M over S, just to make things shorter. Okay. So maximum M for AB is again 8,000. This is absolute value, right? So absolute value of negative 8,000. This, let's write the unit. This unit is pound inch. Pound inch. They're standard, so no need to convert. Oh wait, is it inches? Oh no, foot. Okay, pound foot, pound foot. Foot, foot, foot. Our standard unit is PSI, pounds and square inch. So I need to multiply this by 12 to convert your feet to inches, and then over S. Section modulus of a rectangle is given in our table. It's just BH squared over 6, so let's just copy that. BH squared over 6. Base is 2, height is 4. Please solve. What's the answer? Correct, Trinity. Muni. Sabio. Sabio. Positive. So not negative. Again, absolute value. So correct, Julia. Absolute value. So positive 18,000 PSI. So that's not our answer yet. We have to compare that to the stress that we'll get in section BD. Okay, so for BD, okay, this is 2 inches still, but the height is different. It's now 6 inches. Okay, so equation is the same. M over S, but now our M is for BD. It's negative 16,000, but for maximum, we're getting the absolute value. So negative 16,000. This is again in feet, so times 12 to convert to inches. Over S, S is the same. BH squared over 6, so base is still 2. Height now is 6. Please solve. What's the answer? Correct. Correct, Rika, Miguela, Trinity. Sierra, Sabio. It's positive 16,000. And again, our unit is PSI. So what we're looking for is maximum stress in the beam. So maximum stress, which of the two? 18 or 16? Correct, 18. We're not asking for maximum allowable stress, right? This is just what's the maximum stress being experienced by the beam. So it's 18. And then to be more specific, because this is where 18 is, right? Because this is where our maximum moment for AB is. Okay? Now to the right of B, the stress will become different, right? It would be now for section BD. The stress that we computed for was for stress AB. Okay, so to be more specific, it's to the left of point B. Okay, to the left or just to the left of B. There. And that is number 2. Any questions for number 2? Please answer in the chat. None? Okay, let's move on to number 3. The wide flange shown in W14 times 30 is used as a cantilever beam as shown in the figure. Find the maximum bending stress in the beam. Then given section modulus of your W14 by 30 section is 42 inch cube. So unit of section modulus is inch cube. Okay? So W14 times 30 just means it's a wide flange with dimensions 14 by 30, okay? So we don't have a basic rectangular shape. Alright, so let's solve. Again, what are we looking for? Maximum bending stress. So same process. We need to get the bending diagram to get the maximum stress. Let's continue. So guidelines, there's an applied moment there. So I'm going to write a guideline there. This is a cantilever beam, so there's going to be reaction again here. There's only one applied force, so we can solve for RD. RD is already just 5,000. And then moment. So this creates a counterclockwise moment, 5 times 6, so that's 30K. And then there's an applied 25K load. So the 30K is still greater counterclockwise, so I need an additional clockwise reaction moment to balance everything out. Okay? And then do summation of moment equals 0. About D. Okay, again, negative 5,000 times 6 plus, this is clockwise, so positive, 25,000 plus MD, or plus M equals 0. Please solve what's M. Correct, Audrey. Who else? Correct, Julia. Positive 500. So correct assumption, clockwise, and then unit is pound foot. Okay, now let's do the shear diagram. Downward force, so go downward, 5,000. So this is 5,000. There's no applied force in between, so just go straight. There's an upward reaction, so go up. So this is still 5,000, negative 5,000 plus positive 5,000, you'll get 0. So once again, shear diagram, pretty easy. That's it. Next, moment diagram. Once again, start at 0. There's a downward force here. And then there's going to be an applied force here. So I'm going to do moment at B first. So moment at B equals the previous one. So 0. This is below your diagram, or rather below your 0 line. So that's negative, so minus. Rectangle, so base times height. Base is 3. Height is 5,000. So that's just negative 15,000. Okay. So gonna go down by negative 15,000. Again, 1 degree higher than the previous graph. Next, there's an applied force clockwise. Remember, our sign convention for clockwise is positive. So we're gonna go up. Okay, so negative 15,000 plus 25,000, that's 10,000. So positive 10,000. So that you're gonna go up until you reach positive 10. And then let's do moment at D. A moment at D, so previous one, so positive 10,000 minus the remaining area above your section. So base times height again, so 3 times 5,000. So that's 3 minus 1,000. Sorry, 10,000 minus 15,000, that's negative 5,000. Okay? So you're going to go down by negative 5,000. Then there's a reaction here, clockwise, so you're going to go up 500. Okay? Sorry, moment is 5,000, not 500. Okay. So once again, this is 5,000. Negative 5,000, there's moment of positive 5,000. So negative 5 plus positive 5, you'll get 2, 0. So this is an indicator that you did the graph correctly. Now, we're looking for maximum stress. So we'll get M max. Based on the graph, what's the maximum bending moment? Anyone? Maximum bending moment looking at this graph. Okay, correct. Sierra, Audrey, Bea, Joanne, Paragua. Manrique, 2 points. Okay. Who else? Correct, Aaron. It's 15,000. As you can see, this is the largest value. Right? So 15,000. Unit of this is pound-foot. And then we're looking for maximum shear stress. We're given section modulus, so we're going to use the equation with the section modulus. N over S. Okay, so you can only use M over S if we're looking for maximum stress, okay? Also, we can use MC over I, because this is not a rectangle, it's a wide flange section. So getting the moment of inertia of that is pretty complex. Since also we're not given the actual dimensions of your cross section. Okay, M, positive absolute value of negative 15,000 over. This is feet, convert to inches, so times 12. And then over S. S is given 42-inch cube. So it's in inches, no need to convert. Please solve for this. What's the final answer? Correct, Julia. Correct, Ronel. And Aaron. 4285, 4,285.71. Our units are in pounds and inches, so stress is PSI. Okay, so that's number 3. Wala. Nauna si Aaron sa'yo. Okay. So that's number 3. Any questions for number 3? Please answer in the chat. Okay, since you don't have questions, let's move on to the last topic for this term. Shear stress. So we're done with flexure stress. Next is shear. So this is now our equation. Earlier it's MC over I, or MY over I, or M over S. Now it's VQ over IB. And our symbol is tau since it's shear stress. So it's the same symbol as your earlier topics. So Q is the moment of area above or below the fiber in question about NA. So we already know how to do moment of area, right? It's just area multiplied by distance of centroid to given axis. In this case, it's the neutral axis. B is width of the fiber where shearing stress is desired. So, for example, this is your cross section. We want to know the shear on this point. Okay. So at this position here. Okay. So that's the width. The width of that is B. Shearing stress, we already know. V is shear, shear force acting on that member. And I is moment of inertia. So if you've noticed, same with your stress, bending stress, maximum flexure stress happens at the edge of your member. Here, maximum shear happens at the center. So there's no shear stress at the top because there's no other adjacent force sliding over it. That's how shear stress happens, right? This is free to deform at the top. So there's no shear stress at the edges, maximum at the center. So y1 is distance from neutral axis to fiber in question. YC1 is distance from your centroid of your area above the fiber in question to the neutral axis, and C again is neutral axis to edge of your member. So to make things easier, these are the maximum shear stress for each cross section. So for a rectangle, it's just 3V over 2A. For a circle, it's 4V over 3A. For a round tube, it's 2V over A. And for I-beam, it's V over the area of the web. So keeping that in mind, so these are the shortcuts you can use to solve for maximum shear stress if you have the following shapes. So let's have our last example. The simply supported wood beam in the figure is gluing together 3 160 by 80 millimeter planks as shown. So 1, 2, 3 wood planks by 80 by 160. Calculate maximum shear stress in glue and wood. So we're looking for two things, shear stress in wood and glue. So to get that, we need a shear diagram. So same as before, draw your graph. So this is your 0 mark. Reactions are already solved for. So from 0, we have upward, so go up by 24. This goes down, right, since downward force. To solve for that, okay, since this is symmetrical, it would be pretty easy. This should be negative 24, but to be sure, we can solve as well. So shear at B equals the previous one, which is 24, minus base times height, 6 times 8, negative 24. So C, it's the same. And then there's an upward reaction, so go up, and then you end at 0. There. So next, to get maximum shear, same with your flexure, you'll get the highest point or highest value. So that's 24. Or here, 24. 24 kilonewton, since this is just shear. Okay, next, let's solve. Let's start with letter A. For part A, that's glue, right? So let's draw. So for glue, this is your neutral axis. Okay, so for glue, once more, these are your fibers in question. They are equidistant from the neutral axis, so it doesn't matter which one you choose. Okay, but if it's not equidistant, and you have to choose both, since it's different shear stress in each. Okay, so let's try using the one at the top. Okay, considering this as your fiber. So now you're gonna choose either area above or below. Okay, whichever is easier. Here, obviously, the area above your fiber is easier, so that's what I'm gonna do. And centroid of that is this. And now let's begin. So shear stress is VQ over IB. Let's do it here. V is 24 kilonewton. Q, let's solve. So Q, again, moment of area. Q is AD. Okay? So area is the shaded region. Okay? So base times height. So this is 160. And all of these are 80. So area of the shaded region is 160 times 80, right? And then distance. So that distance would be this. Okay, this is your D. Distance of centroid of shaded region to your neutral axis. So that's times. So this is 40, right? Okay. So if this is 40, I just need to get this amount as well. By the way, I know this is 40 because neutral axis is directly between or in the middle of your middle block or at the center of your middle block. So it cuts your height in half. Total height is 80, therefore this is 40. And I need to get this remaining length, which is also 40. Why? Because total height of the shaded block is 80. Centroid is at half of that, which is 40. Therefore, D is 80. Okay? Let's move this. And equal to 80. We'll put that here. And please solve what's Q. Correct. Correct, Trinity, Aaron, BMA, Pamitang, Vergara, 2 points pa na. Mendoza, and Lavo, 2 points. Julia, 2 points pa na din. So who's the first? Trinity. Okay. So it's 102. 1,024,000. Okay, and then just sub that here. So shear force is B or B max, so that's 24. Convert to Newton, since again Newton millimeters are standard unit, so times 10 raised to 3. Q, just copy this over I. Moment of inertia of a block, use a rectangle. And by the way, it's moment of inertia of the total figure, so that's h cube over 12. So base is 160. Total height is 80 times 3, so that's 240. Cube over 12. B is the width of your fiber, and that's 160. Please solve what's the answer. Correct. Correct, Audrey and Paragua. And Sabio. Manrique. Paragua. Sabio. 0.83 MPa. Okay, so this is for the glue, and then for the wood. Okay. If you saw our diagram earlier, right, the maximum shear stress for a beam is at its neutral axis. So therefore, this shall be my fiber in question. Okay. And then take area above or below. I'll take above. So this is again 160, total height 240. Q is the same, AD squared. So 160 times, this height now is 120, right? Half of 240. This is also 120. So base times height of the shaded region times distance to neutral axis. So this is what I need. And that's just half the height of your shaded region. So half of 120, that's 60. So 80 times 60 times 120 times 60. What's the answer? Correct, VMA, Vergara, and Mendoza, and Pamitan. Vergara. 11,000 or 1,152,000. And then we can solve BQ over IB. B is still 24. So 24 times 10 raised to 3. Q is this, so just copy that. I, same, BH cube over 12. It's still of the entire figure. And then B is the width of this, which is still 160. What's the final answer? Correct, Audrey. And Aaron, Mendoza, Manrique. Tao. Tao. 0.94. Okay. And then I think we can use the shortcut since this is a rectangle. 3V over 2A. Let's try. Okay. So 3 times 24,000 over 2 times 160 times 110. 60 times 40. Yep. So this would be 3 times 24 times 10 raised to 3, again kilonewton to newton, twice total area of your block. So 160 times total height to 40. You'll get 0.94 again. Okay? So that's your shortcut. So that is an or. That is number 1 for shear stress. Any questions? How about the others? Please answer as well. Do you have any questions? Okay, and that ends our lecture for this term. So finally, we have your final assessment to be passed this Saturday, 11:59 p.m. So just answer the following. I'll upload the submission link later for under week 11. So number 1, wait lang. Number 1, what have you learned in this class? So since we're done with all of the topics, what is your favorite? What's your least favorite? Which one stuck with you the most? Things like that. Number 2, what do you think about your overall performance? So you're only left with one quiz, which is this Saturday, modular exam number 3. Coverage is everything I've discussed for module 3. So included your shear flexure stresses. Bakit kayo may conflict of exam at the same time as me? Exit exam. I see. Until what time exit exam nyo? So, okay, you may just answer Mm-hmm. Hindi pa ako nag-check ng quiz 3. Well, ganito na lang. For this Saturday, what if I can just open the whole exam for the whole day? So you have until 12 a.m. to 12 midnight to answer, but you still only have a maximum of 3 hours. A maximum of 1.5 hours to answer your exam. Okay? So once again, I'll just on this Saturday, I'll just upload the exam at 12 a.m. Then you have the whole day to just answer it. But you still only have 1.5 hours. Okay? And don't forget to upload your solution as well. So no Zoom meeting anymore this Saturday. And then what else? Yeah, no Zoom meeting. And then what else? Di pa ako nag-check ng quiz 3. Yes. If you submitted at 7:30, please send me a letter. That's too late. 4:30 is the deadline. So send me a letter. Why are you so late? Okay. I'll check the late exams later. Yeah, if it's a minute late, that's fine. Don't send me a letter. I'll just check it manually. Again, for 1 minute late, it's fine. Yeah. For if you uploaded your exam or submitted your exam at exactly 4:30, Blackboard counts that as late already. So that's fine. Don't worry about it. I just have to manually check those attempts. So that's why it's still not showing up because I haven't checked yet. Okay, any other concerns? I might have missed something. If I didn't answer you yet, you may repeat your question. By the way, this Thursday, group activity, hopefully. As of now, we'll have a group activity this Thursday for your last chance to get additional points for your modular grade. So groupings are the same as last time. If you don't have a group mate yet, talk to your classmate and tell me on Thursday what your group is. Okay na? No more concerns? Again, modular exam this Saturday, no Zoom meeting. Answer within the time frame 12 a.m. to 12 midnight. 1.5 hour for submission after. And then group activity this Thursday. Alright? Okay, since you don't have any more questions, you may go. See you next Thursday. Goodbye, class.